Hello again. So, welcome to class, our second ever class of in-person class, because all of the stuff before didn't count. So, let me just, well, yeah, I think there's announcements. All right, so last time we were talking about if statements, elif statements, and we went through a number of examples regarding the divisibility of numbers, which should also help hammer home all of this information about modulus. And incidentally, if any of you have seen the video that went up yesterday, I apologize for the audio quality, but if you listen to that, there's nothing I can do about that. And that's going to throw off the audio quality no matter what we're doing. And even if you turn that fan off, this lecture theater up right on top of it is actually a huge HVAC unit, because that's the roof up there, so like it's kind of, yes! Do I have a microphone? I think I might have a microphone. Let's see. Maybe that helps. Yeah. I got a pretty good projection voice, but you know. The mask certainly doesn't help. Testing. Is that better? Excellent. How's that? Is that better? Are you picking up anything over the amplification at all? How do I sound in the back?
So good.
Excellent. All right. So we need to keep moving with this material on account of the snow day, so we'll just kind of breeze through this. So I'm going to skip the next section, which is on Spectre. It's an example of a bug that existed at one point that's now been fixed, so you don't have to worry about it anymore. But it involves branch prediction on if statements. One of the ways that modern CPUs with multiple processors speed up execution is by predicting the results of if statements, predicting the results of those branches executing, and then it just kind of goes with the prediction, which it runs on another processor. And if you do, like if you take a look at the code at exactly the right time and you stall it, you can actually read information that doesn't belong to you, which is a data breach, which is what the Spectre bug was about. I'm going to skip this section because we have to keep moving, but you're all free to review it on your own time if you want to. And I've done plenty of runs through of the Spectre material on previous offerings of the class if you look up the YouTube channel. So, let's move right along to linear search algorithms. So this is kind of, we're dipping our feet now into a completely different topic, sub-genre, sub-discipline within the confines of computer science called algorithms research. So, you know, writing an algorithm is one thing. Doing research on algorithms is an entirely different thing. There are many different ways in which we measure algorithms. There are many ways we compare algorithms to other algorithms. And in general, like many papers, if you want to go on in your career to become an algorithms researcher, you absolutely can do that. But, you know, as with all things, we need to start with the basics. So, one very well understood class of algorithms, sort a problem that often needs to be solved in computing is how do you find stuff inside of other stuff? The most basic approach to this problem is called linear search. Under linear search, you have a data structure. You're looking for an element inside of that data structure. And the linear search algorithm itself is you just check every single one to see if it's the thing you are looking for. If it is, then you return a true result, or you return the position of the thing you were looking for, or something like that. And if you don't find it, you only know you didn't find it because you looked at all of them, including the last one, and you didn't see it, right? Make sense so far? So, an example of this, you might want to find the first location of a character inside of a string. You might want to find a number inside of a list of numbers, etc., etc. So, we actually have a couple of ways of going about this. Number one, we have the index method, which can be applied to many different types of data structure, including strings. Another way we have solving for this is the in operator. So let me just pull up the terminal here and we'll take a look at it. Since I've figured out how to get my actual computer on here, we can actually do some code examples. So let's say I had a string, like, everything and nothing. If I wanted to find the location of the first n, for example, s.index n. The location of the first n is index 8, so if I say s at 8, oh, that's a star, never mind, 8, oh, there, good, you get n. Very, very neat string. So far, so good, right? Nothing should be, too bad. Another way that you have of going about this is what you need is a Boolean result rather than the actual index. You just, you say n in s in Python, and it'll return true or false. So one question you might have, well, what if n is not, what if the thing you're searching for isn't actually in there? You actually get a value error. So index will fail if the thing you're looking for isn't in the thing. This is enough to kill your program. We're going to learn how to deal with exceptions around topic 6, so we'll put a pin in this for now, but, it's usually a good idea to try to make sure that the thing you're looking for actually exists, but it's not, there are ways of getting around it. So, good. So, the question would be, how would we go about implementing this if we had to ourselves? Any ideas? Anybody? Let's go from the most granular perspective here. We have learned about if statements. We have learned about while loops. Which of the two of those would you say will get you closer to an implementation of linear search?
While loop?
Yes. When you have a data structure, you have to, you want to examine each element of the data structure in sequence. In order to do that, you have to repeat things. If you're repeating things, then you should write a loop to do it. And this sort of brings us into a very common loop construction, which is that of looping over the elements of some sort of data structure. It's so common, in fact, that Python has specific ways of dealing with it that require a lot less work, which we're going to see at the end of this lecture. But for now, let's examine the implementation that you would perform if you were to do it just with while loops, right? So So we're going to look at this with for loops as well, but we'll come back to it. So we are performing linear search over S and C, where S is a string and C is a character. We set I equals to 0, while I is less than the length of S, and S at I is not equal to C, increment I. So this is an interesting thing, right? One of the things that this loop does, which we haven't seen yet, is it's not just stopping when it reaches the end. It's also possibly stopping when it finds the thing it's looking for. That's the purpose of this second clause, right? Make sense? Good. So, this might be slightly confusing to some of you, but this loop only then contains the one line, right? This I plus equals 1 is the only line of code which is contained by the loop, because it doesn't need anything else, right? So, this if statement actually only executes after the loop has terminated. So, once the loop is terminated, we test to see if I is less than the length of S. If I is less than the length of S, we know that the loop exited before it reached the end of the data structure. We can therefore infer that it found the thing it's looking for. This is kind of coming at the idea of we found the thing sideways, you know. The fact of whether or not the thing was found is encoded in the value of the I variable. This is a slightly less explicit way of going about it. You might, you know, if you were a little bit more, if you wanted that more explicitly, what you could do is you could set a Boolean variable up here. Something like, I found it. And then, okay. You could set an if statement inside of here that sets that from false to true, and then later on you can test the value of that Boolean variable. That's another way of going about it. That kind of makes the, you know, the condition of whether or not the thing was found a bit more explicit. But this is also a completely valid approach. So, in the case where the thing exited before it reached the end of the data structure, we return the value, the index at which it was found. Since the loop is breaking, as soon as we found the thing, I is no longer incremented past that point, so the value of I is actually the index at which the thing we were looking for was found. So we can just return it. Otherwise, we return false to indicate that this thing did not find the thing we are looking for. Any questions? Yep. Oh, yes. I'm sorry, could you speak up, please? Yeah. Yeah, so that's a good question. So the character that we're looking for, if it's at the end of the string, does this still work? That's the question. And the answer is yes. So if the character is at the end of the string, right? If we just trace this in our brain, let's imagine that the last index, the last valid index in the string is 5, right? So I will have a value of 5. S at I will be equal to the character, so this will not execute, right? If, on the other hand, the last element was not the thing we were looking for, this line would execute. So then I would become 6, and on the next test of the loop condition, this is the condition that would fail. When you got here, you would get so it's it all hinges on the fact that things are 0 indexed, right? So for a data structure that contains 6 elements, 5 is the maximum index, right? So in order for this to not be true, I would have to be, in that case, 6 or greater. So it would have had to have undergone this step, right? So yeah, so it still works. Good? Good. Any other questions? Excellent. So we're going to go through a few different variations on this. So this is a variant which returns the value that we are, this returns the index as soon as it's found. So you can see the condition on the while loop has been split up into the first bit, which stays in the while loop, and the second bit being attached to an internal if statement. So if s and I is equal to c, return I. This is immediate exit from the function. Otherwise, everything is more or less the same. This, however, does bear a little bit of explanation, because, like, this construction bears some explanation because you should become familiar with this type of construction. Essentially, we run through every element of the data structure, testing for this condition. If this condition comes out true at any point, we return immediately. That means we only get here if this condition was never true, right? So this is like a catch-all, in the same way that an else on an if-else case is a catch-all. This catches all cases where this condition never came out true, right? So this is actually a fairly common way of going about it, actually. Yeah. Any questions? Yeah. About which, sir? Oh, sure. Yep. 0, 1, 2, 3, 4. Yeah. That's a very good point. And yes, that's actually very common in C-based languages for that to be the case. So, what your very astute and esteemed colleague has pointed out here, let's imagine that we're right at the end of this, right? So again, let's go back to this example where the maximum index is 5 and the size of the thing is 6, right? So let's jump to the bit where I is 6. So this condition fails, sure, but if the program tries to evaluate this condition, it will produce an error. Why? Yeah.
Out of bounds, the range, the index out of bounds, error, blah, blah.
Yes. So if you try to access something that is not inside of the data structure, that will result in an error, right? It's called an out-of-bounds error, because you're exceeding the bounds of the data structure. So this is what it's actually doing under the hood. The computer knows that for things that are joined together with AND, only one of these things has to fail and the whole thing fails, right? So the execution of this statement, or this expression, sub-expression technically, is conditional upon this one coming out true. Some languages do this, some don't. Generally speaking, I would say relying on it is an unsafe practice. So, if you wrote it that way and you didn't even realize that you wrote it that way and it all works, then it all works, because you have to implement it for the language that you're implementing it in. But generally speaking, you shouldn't rely on that transferring to any other language. But yeah, that's a really good point. So, good. So, now we're going to introduce a new instruction to you guys. We have an instruction which can break you out of a loop. It is called break. As soon as the execution of the program hits a break statement, the loop is terminated immediately and execution jumps to the end of the loop. Break statements aren't extremely common, but they do have their uses. So here's an example which combines the two approaches. The loop is exited immediately upon this condition coming out true. But rather than just immediately return the value, it breaks you to this point, and then you execute this if statement as in the first example. So why would you ever want to do this? Because this, of all the examples we looked at, this is the longest so far. So does anybody have any idea why this might be useful? You, sir.
It addresses the problem that was mentioned earlier about it has to be in range.
Yes. So number one, it addresses this problem that we just had on the previous slide, because we're not having to test this condition and that condition at the same time, theoretically, even though we aren't. There's another one, though. It sort of relates to the spaghetti code point that I was making last time. Yes?
So sometimes they make up the
Could you shout that, please?
So sometimes they make a infinite loop, then you just do this stupid.
Yeah, not what I was looking for. So with this one, even though there are two return statements here, we have one entry point and two exit points that are so close together they might as well be one exit point. Where we were breaking from the loop immediately, that provides one exit point to the algorithm for each iteration of the loop. We don't even know how many exit points we would have from the algorithm. It's dependent on the size of the data structure. So if you're the type of person who's fussy about that sort of thing, this would be your approach. Good? Good. All right, so having undergone that painful lobotomy, let's now do the for loop, which is the thing that everybody uses because it's much easier than the previous approach. So, for loops. Oh, okay, so here's a question. How many people in here have used programming languages other than Python? How many people have used C, C++, or C#? How many people have used Visual Basic? How about Java? Are there a number of Java people? Okay. Okay, who knows a language that I didn't say? Just shout it out. Haskell, oh geez. R? Okay, I guess I'll accept that as a programming language. I mean, really, it's a statistical package pretending to be a programming language, but you know. Anyway, MATLAB? Yes, MATLAB is, you know that MATLAB's syntax is actually based on Fortran, which is one of the earliest programming languages.
Oh, I need both of them.
Yeah, there you go. Fortran 77, my friend. So, for those of you who have used other programming languages, for loops in Python operate very differently from any for loop that you would have been used to so far. So I'll give you an example. Piece of chalk. So, this is what a for loop looks like in C, and most languages follow the C standard. For int I equals 0, I is less than x, I plus plus, and that's getting a little close, but then you do stuff. And this is C syntax. So in C, you have to declare the data type of variables, and you start and stop everything with curly braces, but otherwise, essentially what you're doing is you're taking this statement, that statement, and this statement, collecting it all on one line. That's a for loop in every language except Python. In Python, a for loop is bound to a data structure. What a for loop does in Python is it takes every element of a data structure and iterates over it in sequence. So, if you have a list, the first loop iteration is the first element of the list, the second loop iteration uses the second element of the list, etc., etc., etc. So, like all of the data structures that we're going to cover in this class, all 5 of them, can be used in for loops in this manner. So that's sets, lists, tuples, dictionaries, and strings. So, unlike the while loop, you actually don't have a lot of fine-grained control over things like the exit condition or the incrementing mechanism. As a result, it's actually fairly complicated and difficult to get things into infinite loops. They are considered to be safer. It actually, it's not impossible to get into an infinite loop with a for loop, but essentially, in order to be able, that's a question for the class. Who can think of a way to get a for loop in Python into an infinite loop? Yes, sir?
You could maybe iterate over like a list or something and keep appending items to the list and then keep going.
Yes. So if you have a data structure that is growing as you are iterating over it, if it's growing faster than the for loop is knocking cases off, then it will not ever terminate. But, that's kind of a, you have to be trying hard to be able to do that, so, yeah. So, let us compare 2 programs. The program on the left uses a while loop, the program on the right uses a for loop. So this is a fairly simple program. We have a string potato, we iterate over it, and print each character in it in sequence. So I is equal to 0, while I is less than the length of s, c is equal to s at I, print c, I plus equals 1, and then you're done. The for loop, on the other hand, s is equal to potato, for c in s, print c, and you're done. So the reason that this one has been written like this, one might say, could you not just take this expression here, plug it in there, and call it a day? Well, if you're going to go that far, you might as well say, why don't you just print the string normally, and then we don't have to do any of this, but you can laugh, that was a joke. So, the point here is that this assignment is implicit in the for loop. So this step is going on inside of the for loop for free. So semantically how this works. For c in s means for some specified data structure s, in this case, we are going to call each element of it c for the duration of one iteration of the loop. After that iteration is finished, we shall replace the value of c with the next element in that data structure. So if the data structure was a list that contains 1, 2, 3, 4, and we plug that in there. C would have values 1, 2, 3, and 4 on successive iterations of the loop. Any questions about that so far? Pretty straightforward, right? Not too bad? The amount of time that this saves is absolutely astonishing. Incidentally, other languages like C# I know have the equivalent of this going on, but they call it a for each loop. So that's the way that they distinguish the C-style for loop from the Python-style for loop, is by calling the Python-style for each. Does that make sense? Good. So, the body of the loop should not modify variable, or you can get infinite loops or string behavior. Yes. So, the cardinal rule of for loops, if you're looping over S, do not modify S inside of the loop. For example, let's say you have a loop and you're iterating over, 1, 2, 3, 4, 5, and 6. Let's say that inside of the body of the loop, you delete the next element in that data structure. Your loop is going to be skipping elements, right, relative to how you put it in. And that may or may not be what you want. It's basically, it's like, just don't touch it, because, like, while it's possible to predict how it's going to deal with a situation like that, you probably don't want to be put into a situation where you have to predict how it's going to deal with a situation like that. So it's safer to just leave it alone. Make sense? Good. So that's actually, that was true in an older version of Python, but it's no longer true that I is undefined after the loop. It used to be that the loop variable was bound to the context of the loop that couldn't be accessed outside of it. That's actually no longer true in current iterations of Python. Slides need to be updated. So, good. How are we doing for time? Oh, we're doing fine. So, the range object. So, range is kind of like, it's a way of generating data structures on the fly. So if you need a list of elements from some number to some other number, range is your boy. So if you provide it one argument, some value n, they have to be integers, it'll generate a data structure from 0 up to n minus 1. So if you're trying to generate, say, a list of indexes corresponding to the number of indexes in another data structure, all you would have to do is say, range length of that other data structure, and that would give you a bunch of indexes. If you specify 2, you start at A and you go to B. Well, B minus 1 anyway, right? So you can optionally specify a starting point. If you include a third argument, that tells you how many to count, how many to step by. So this is just I'll give you some examples. You have to convert them to a list to be able to actually look them. But say range 50, 0 through 49. 25 to 50, 25 to 49. Count by 2s, you're counting by 2s. Make sense? So using this, you can generate a nice, neat little data structure all in one line, which the for loop iterates over. Yes, the class was important. Maybe they were in the wrong class and they didn't want to say. Yeah. No, you can't generate floats in the same manner. You have to write another function that did that. Yeah. Actually, we have an example of that coming up when we talk about database, or not databasing, visualization techniques. Later on in the course, we actually write a function that does that. Good. So I'd like to request that if you guys are going to talk to each other, if you could please just keep the volume down. It's loud enough in here without the with that bloody fan, without having to worry about that being picked up on the recording as well. So, range object generates a sequence of numbers. Arguments must be integers, and you can convert them to another thing using conversion, as I demonstrated. So, for example, this piece of programming prints all of the even numbers between 0 and 50. Yes?
If you don't specify a data structure, like what is it by default?
It'll give you a syntax error. You have to specify a data structure. So, linear search using a for loop. Remember how I said you could create a list of all of the indexes of the things? Here is that example. So rather than using a while loop and iterating over, I is 0, I is 1, etc., we generate a data structure that contains all of those indexes. We for loop over that, making the loop variable the same I as before, and then we can essentially run the same algorithm, but with 2 fewer lines and with much, much less possibility of screwing it up and causing an infinite loop. Any questions? Good. So, we can also use for loops to rewrite our factorial example. So, for some factorial n, if we have the accumulator f, we can just for loop over the range 2 to n plus 1. Remember that the range, the second element, the thing you're going to, it actually stops 1 before that. So that's why we need to put the plus 1 in there. But otherwise, that's exactly the same algorithm. We just don't have to do all of that bookkeeping with respect to the counter, which is extremely useful. So let's talk about some common ways in which loops are not done correctly. Things that can mess you up but good. So, number 1, incorrect indentation. Remember that in Python, the indentation level of the statements has semantic content. That's how you tell what is inside what other thing. If you mess that up, you'll screw up your algorithm in a lot more ways than just getting your loop. That's a much bigger problem than just loops. So, a very common one actually is using an incorrect termination condition. The whole less than versus less than equals problem. Even the best of us make that one, and frequently, this is why we test things. Whenever you write a loop, and you're trying to test to see if that loop works, you should always test it such that it hits that final exit condition. At least in one of your test cases. If you're hitting that final condition, you'll know whether or not you're using one of these when you should be using the other. Make sense? So, infinite loops we've talked about quite a lot. Off by 1 errors are another big one. So, it's sort of related to the less than equals problem, but if you have a variable, like an index, and you're trying to iterate over the elements of a data structure, whether or not you're like you should be on element 5 or 6 or 7 or 8, like that can be difficult to keep track in your brain. It's just one of those little things that human beings have trouble remembering. So again, testing. And then also, oh, I talked about that one when I should have been talking about that one. Yeah. So anyway, incorrect initialization as well, like the setting f equals to 0 problem. Any questions? Good. So, here is a function. How many errors does it contain? I'll give you guys a minute. How many people think A? How many people think B? How many people think C? One guy at the back, okay. How many people think D? How many people don't know? So, who's got an error? Who can point out a problem with this program? You, ma'am. There's not string quotations around the, which? No, that's correct. Yeah. In Python, single quotes or double quotes are interchangeable. Yeah, it's not testing to see if it's equal to a particular value. It's to see if it's the literal character n. So it's counting the number of occurrences of the character n in a string. Yeah. Didn't give x a value. Yes. X is uninitialized. So when we try to use it before it's been assigned to, that will be an error. That is an error, number 1. Now, yes?
It shouldn't be like less than or equal to, it should be just less than.
Also true. This should be just less than, not less than or equal to. Otherwise, you'll get an index out of bounds error. Who's got another error for me? Yes?
I equals I plus 1 shouldn't be in the if loop.
Aha, that's... So this guy should be in one indentation level back. Still inside the loop, but not inside the if statement. So because of that little error, actually, the behavior of this program is kind of interesting. It will only actually terminate on strings that contain only the character n. As soon as it hits a character that's not n, it stops incrementing the counter and is stuck forever, which is kind of interesting, I think, anyway. So yeah, anybody else got any other errors? No? Well, the correct number of errors is 3, so I was testing you in that. There you go. Very good. So, just a quick recap. For versus while loops. For loops automatically initialize and increment the loop variable, thus avoiding certain classes of errors. For loops may necessitate jumps out of the body of using break or return statements. So we didn't, there's a third one actually that we didn't talk about called continue. A continue statement just pops you to the next iteration without having completed the one that you're on. Most of the time, if people want that functionality, they just use if statements to achieve it, but you can also, like there's a construct for that as well. So, yes. While loops allow a single exit, and make the termination condition explicit. For this reason, we avoid the break and prefer a single return statement at the end of the function. It just makes things more clear. Any questions about any of that? So everybody's going to get 100% on assignment 2 then? Yeah, there we go. Awesome. All right. Good. So, might as well get into the next topic then. I know there's only 3 minutes left in class, but yeah. So, lists. Like we gotta use every minute that we have because that friggin' snow day, man. Who knows? We might even have another one on Friday. Jeez. So, lists. So we're going to talk about data structures in a little more detail. Lists are like tuples, but they are mutable and not immutable. This makes them more useful generally. So, like tuples, lists are ordered collections. Elements don't have to be of the same type, and elements can occur multiple times. The main difference is that they are mutable and can be updated. Lists use square brackets, whereas tuples use parentheses or round braces. So, the main difference here, if I have a list, you probably see me use a couple already. So I can do something like this. And it doesn't give you an error. In a tuple, that would have given you an error. From a practical standpoint, that's the main difference. Otherwise, they're actually very, very similar to tuples. Most of the difference between the two comes with the way in which the lists and the tuples are stored in memory. So this is going to get a little bit like computer architecture-y, so I hope you'll bear with me for the next couple of minutes. But so one might say, if the tuple can't be modified and the list can, why on earth would you ever use a tuple? Fair question, right? The answer is memory efficiency. So the manner in which computers store memory, basically you should think about it as like a giant table, right? So the way that it works, when the computer declares a data structure, it says, okay, I'm taking from this to there, and I'm calling it, my list. Right? So the trick with tuples, like the thing that makes them faster, because tuples are faster than lists, the size of this is known upon creation and does not change. So the memory that it occupies never has to move. Whereas, let's say you had a list like this and you drop a great big fat string right in the middle of it, right? Actually, this wouldn't work. It's more like for appending. I'm going to change the example. Let's say you had a list and you appended a great big fat list onto the end of that list, right? So you have a list, right? And you have to put another list on the end of it. Well, what if, my friends, this is already used, right? The memory is already occupied. So what you have to do is you have to pull this whole guy up and put it somewhere else where it does have room for itself. And it may not seem like it, but these types of memory swapping operations really can accumulate in terms of performance if they get out of hand, particularly if the data structure is very large. So because the tuple never changes its size, it never has to be moved. So it never has to have these types of dynamic allocation scenarios. So that's why people use tuples. But lists generally are more useful and easier to use as a beginner, certainly, and I recommend that you use them as often as you can. Class dismissed!